Okay, good morning. I hope you can hear me. Yes, thank you. Thank you for saying good morning. Okay, that means thank you. This is the last live session. I mean, we will have the review session, but this is the last session, which is covering a new material. Okay. I mean, this week is the last week. That means we will have session today and we will have session tomorrow. And what we will do, we will start another part of chapter 10, and we will talk about the polar coordinates. Okay, that we have to know what is the difference between the Cartesian coordinates and the polar coordinates. We have to know how to plot the point, and then how to plot the curve in the polar coordinates. And also, we will try to find the area of the region which is bounded by the polar coordinates, polar curves. Okay, that means that's the few things. Today, we will just try to learn how to plot the points and a few curves. And tomorrow, we will take care of the area. Okay, that means what we have. Polar coordinates are definitely different than the Cartesian coordinates, because the Cartesian coordinate just XY plane, and we're looking for the perpendicular distance, like a right angle distance. We know we moving along the X and along the Y axis. Polar coordinates are a little bit different. We will still have a plane, and we will kind of adopt the XY plane, but we will look at different things. We will not look at the distance from, the perpendicular distance in the horizontal direction, which is distance from y-axis, or the vertical direction distance from the x-axis. We will look a little bit, from a little bit different angle, I can say. Okay? And let's see what we have. I can show you this. Okay, that we can see Cartesian. I found this picture I don't remember when, many years ago, but I love this picture. This is Cartesian bear, poor bear, of course. Everything is right angle, right? We can probably put some points and find the corresponding coordinates. Yeah, but the polar coordinates, we can see how nice and smooth and round. Polar curve will be like lots of curves, and we will be able to find an equation, of course, from different systems. Okay, that means it's more rounded, okay? Not like a straight lines. Okay, let's start. In what we have, polar coordinates. Actually, did you like the bear? Let me show you one more time, because nobody comment. Do you like the polar bear or Cartesian bear? You like bear? Okay, yes, okay, yes, yeah. Okay, good, okay, yeah, it's a really, really old picture. Yeah, I don't remember when, but yeah, it's old picture, but I love it. Okay, that means polar coordinates, what we need. For the polar coordinates, we will need at least one reference point, right? Because if you will even imagine the bottom of this slide, the white plane, if I will put a point, yeah, how do I know the location of the point? Yeah, I don't know. Is this point I don't know, far away from my reference point? Has negative, positive coordinates? We don't know. That means what we need, we always need some a beginning. That means we will have in the polar coordinate system, we will have a polar axis, yeah, which is just half of the line. And that point, which normally is the origin, we will call a pole. Okay, that means this is the pole. And this one is half of the line, and we might read this, we might correspond this to the positive part of the x-axis from the Cartesian coordinates, which means I can add the y and I can add negative part. Okay, But we can see I shouldn't really put, like normally I will put something like that. No, we don't really have y. We will make the connection between x, y, and the polar coordinates, but that's later. Okay, that means for the polar coordinates, we need reference point, which is like an origin, pole, and we will need like a starting line. Okay? We will call like a polar axis, which is this one, the positive part of the x-axis. Okay, and I have this nice picture. Let's see. And I can add this, which actually you will always see me writing both of them, because ironically, they are extremely helpful, okay, these lines. Okay, and again, this is not really negative part, it's just like making more reference like points on the plane. Okay, polar coordinates, what we need. Polar coordinates are r and theta. Okay? That means starting from my polar axis, the polar axis will represent, because what we have in the polar coordinates, we do have an angle. Okay? We do have an angle, and we do have this certain type of the distance from the origin. Okay, that means polar axis will represent a 0 degree. That means this is my initial point. Okay, this will represent 0 degree. And then we do have this feeling from the unit circle, from the trigonometry, right? That if I would like to indicate another angle, positive angle, I will go counterclockwise direction. And we can see, like theta, yeah? Let's say theta is, I don't know, around 45. That means this is 45. And then if I will keep going, this will represent 90, correct? Of course, we will use radians. That line will represent pi, 180. This line, this angle will represent 270, and back to the full revolution, 2 pi. And as we can see, that's the reason that these lines are quite helpful, okay? And I can, of course, draw every like line which will represent 360 like degrees angles. Okay? But that we can see, we have to indicate a line with the corresponding angle, and that will be theta. Now, what r means? R means the distance from the origin, from the pole, to my given point on the line which represents my angle. That means, for example, let's maybe find, let's say this distance is, because we don't have the scale, let's say this distance is 3. 1, 2, 3. 3 units. Okay? So now I would like just 2 units on 90. Okay? That means this is my 90. I will use different color. That's my array, or that's my like angle 90, and I need 2 units, 1, 2. This is my point 1. Let's maybe try 1 unit on pi, on 180. That means I have to find 180, that's 180, that's my angle, and 1 unit using this scale is here. That means this is my second point. Maybe one more. Let's say 1 unit on 3 pi over 4. And that means I have to find 3 times 45, 1, 2, 3, this will be 3. We know it's exactly the same, the angles are exactly the same like from the unit circle. 1, 2, 3, that's my angle, that's my theta. 3 times 45, and just 1. This is my first point. Okay, that's actually the polar coordinates. We did plot a few points in the polar coordinates. We need like an angle, and we need a distance on that angle, on that half of the line, the array. We need a distance from the origin. Okay, that means r represents the distance. We can say OP, and theta represents the angle. Okay, and we will call polar coordinates the ordered pair. And you can notice which one is interesting, P sub 2, the second point. we have the point here, yeah, and it's 1, it's positive 1 pi. Yeah? No, I mean, at the moment, we still have negative values, but I can explain how we can extend this to the negative radii and negative angles. Okay, I think that's pretty much everything for today. No, let's stay with me. Okay, that means what we can have. First of all, a negative angle. Probably that's not a problem because we remember the positive and negative notation. I will put this. Indicating, like drawing an angle with like the positive angle, we will always go counterclockwise direction, like I just did. Yeah? I can even put this again. 0, 90, 180, 270, and 360. 3 pi over 2 and back to 2 pi. Yeah? But if we would like to indicate, like, let's say I want theta to be negative pi over 4. Okay? And we know also from the trigonometry that we will go clockwise direction, starting from my polar axis, of course, from my reference line. That means this is 0, negative pi over 4. I will go clockwise direction, and this is negative pi over 4. And now the first question for you, negative pi over 4. Or maybe we can plot 1 second before the question. Let's plot the first point. Let's say the same 1, negative pi over 4. I have to find my angle, negative pi over 4, which is that green line, and just distance 1. Let's say this is 1. I will remove this piece up 1. Okay, good. But now, do you think the angle negative pi over 4 can be defined using a positive notation of the angles? What is the other, like what is the corresponding, the relevant value of the pi over 4 using a positive notation? Can you give me like the same, I will draw the same line, but I will use the positive notation. Yeah? Let's start from the 0 and let's go this way. That means what is the measurement of that angle? Right? We can count 45, 1, 2, it's 2 per quadrant. 1, 2, 3, 4, 5, 6, 7. 7 pi over 4 is actually the same angle. 7 pi over 4. Okay? As we can see, it's getting interesting, because now if I will ask you to plot the point P sub 2, 1, and the angle is 7 pi over 4. Okay, where is that point? Do you think you can try to help me? Where is that point? 1 for the 1 is the distance from the origin, and the 7 pi over 4. Oh, are you there? I think you're there. We do have some participants today. Yeah, it should be exactly the same like P sub 1, the P1, because angle negative pi over 4 or 7 pi over 4 positive is the same. That means this is the same angle. The same point. That means you can probably realize, because of the notation of the angles, and the angles are kind of like they repeat every like 2 pi, it's periodic like situation. We may have for one single point, we may have infinitely many like representation, the coordinates representation, because now I can add 2 pi and I can be at the same point. I can add another 2 pi and have the same point. That means I can rewrite angle for so many ways, right, that we can see. And of course, the distance will be still 1. And this is not possible for the Cartesian coordinates. For the Cartesian coordinates, if I have X value given, Y value given, that's it. That's one unique representation. For the polar coordinates, because of that positive notation, negative notation, I may have few different representation for exactly the same point. Yeah, like this one, P sub 1, P sub 2. Okay, that means that's the interesting. Okay, that's you confident, I hope, with the negative and positive notation for the angle. Now I will add a negative notation for the radius. Okay, that's mean what this means. Let's see. I have a nice thing. I will still add 90 and 180. 0, 90, 180, 270. Okay, because we have to be confident, yeah, with all of these angles. Okay, and now having a point, let's say this is 2 pi over 4. That's my point. Distance 2 and the angle is pi over 4. I want this to be P. Okay. Now, if my point is -2, defined, the coordinates are -2, what this means? I simply have to, like if I see the negative radius, if you see the negative radius, you still have to draw the angle pi over 4, and then you have to like make the angle, like you have to elongate, you have to make longer, you have to draw in the opposite quadrant. And opposite quadrant means for the first one, of course, the opposite is the third one. For the second one, the opposite is the fourth one. And opposite means something like if you looking like in front of you and you will turn 180 degrees, you will be looking in the opposite direction. That means we simply mathematically, if you would like to see this, we have to add 180. We have to add pi to the angle. That means if this was 45, this will be 225. I'm just adding 180. But like physically, practically, this means that we're turning backwards. Exactly. Or you can think we're just making longer and this is my opposite quadrant. And now on that opposite line, I will indicate the distance 2, which of course this will give me -2. And still, but please note, the angle is still the original angle. The -2 is telling me that I jump to the opposite quadrant. Okay? That means the negative radius is telling me that I am in the opposite quadrant of the original angle. Okay, and we can possibly use the same plane, -1, and maybe, okay, I can actually say 5 pi over 6. Right? So I have to find an angle at 5 pi over 6. 5 pi over 6 is 150. That means I think it's this one. Okay, I can maybe write like that. Let's say 2, -2. I just don't want to be too close to the origin. So -2 will be here. Oh, hang on. This is just 2. Let me say 2, 5 pi over 6. But now my point, P sub 3, is -2, which means I will simply make a line longer. And like theoretically, I'm adding 180. I'm adding 180, and then I am indicating the same 2, like the distance from the origin must be 2. But this will be -2 and still the angle. But the angle is from, if the radius is negative, the angle is from the opposite quadrant. Always, if the radii are negative, the angle will be, the position of the point will be in the opposite quadrant than the given angle. Okay, that means this is my point P sub 3. That means this is the way This is the way to deal with the negative r. Okay? I will call a radius or distance from the origin, but since it's r and everything is like circle-wise, it's like a radius. Yeah, as we can see, if the radius is positive, always the point will be in the same quadrant. If the radius is negative, opposite. And we know what opposite means. First and third, second and fourth. Yeah, adding pi. Turn it like 180. Okay. Yeah, we know almost everything. Now we have a few points, which I didn't really name them. Oh, we can name them A, B, C, D. We have these points, and we have to plot these points in the we have to plot them. Okay, we have to just plot these points, and they are defined in the polar coordinates system. Okay. Let's say point A. Do I have? Okay, I do have the solution on the other side, on the other slide. Okay. Okay, 5 pi over 4. I need that angle, 1, 2, 3, 4, 5. That means this is my angle, 5 pi over 4, and I need distance 1. Let's say this is 1. This will be point A. Okay, now B, okay, 3 pi. 3 pi means 2 pi and 3 pi. It means actually it's corresponding. This is the angle 3 pi, and the distance 2, 1, 2. This is the point B. C, oh, I have negative angle, negative 2 pi over 3. That means 2 times 60. This will be 1 times 60, 2 times 60. That means I'm going in the negative direction, clockwise direction, negative 2 pi over 3, negative 120, and the radius is 2, 1, 2. Okay, and the last one, and you notice I didn't put the arrow on the y-axis because we don't have the y. Okay, 3 pi over 4, 3 times 45, that means that's my angle. However, the distance is, the radius is negative. I have to make a longer line for the corresponding angle in the opposite quadrant, and 1, 2, 3. This is my point D. Right? We make sure that you can pause the video even before me drawing, and you can try to draw a point. Because the main point of this session is to be able to draw a curve, the polar curve, because they are so nice, beautiful, like round shapes. Yeah? Okay, that's the points. Okay. Okay. And now this is the comment. We notice, we actually just went through this, that each point can have infinitely many representations in the polar coordinates, not in the Cartesian. And for example, this one, okay, I found a few few coordinates, but if you will probably guess, each of them represents the same point. And let's try. Do I have, okay, I have the solution down there, but we will see. Okay, 5 pi over 4. It's 5 times 45. 1, 2, 3, 4, 5. That's 5 times 45. Okay, 5 times 45, and the distance 1. Okay, so this is point A, B, C, and D. That's point A. Now, I need okay, negative 3 pi over 4, I will go clockwise direction. That means I will go this one, and we can see 1, 2, 3. That means this angle is definitely negative 3 pi over 4, and distance 1, the same point. Now 13 pi over 4. Okay, let's count by 2. Okay, 13, that means and it's positive, I will go counterclockwise direction. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I mean, this will be, how can I indicate this? I went once and twice. That's 13 times 45, okay? And that's the end distance 1, the same point. Now, the point D has the angle 45, which is this, but the distance is negative. It will be, oh, should be nice line. This, like, yeah, my 45 is not exactly symmetric. The negative radius I will draw instead of here. I'm not drawing here. I will draw on the opposite part, which this is the point D. Okay? I can't here write the angle. Okay, that means we can see infinitely, we can create infinitely many coordinates just for one single point. Okay, that's my drawing. Okay, now what we will do, because another way that we have to be like confident with both of them, we have to make a connection between the polar coordinates and the old Cartesian coordinates. And what I did, I draw a point, right, in the x, and I mean in the plane, but I named the point xy, meaning of course Cartesian coordinates, and r theta, thinking about polar coordinates. That's the same point. Okay? And now one of the questions that we have to know, how to convert, how to change from xy to r theta. This means that we need a few connections between r theta and xy. That means what we know, x and y are the perpendicular distances. You can see this. R is the distance from the origin and theta is the angle. That means looking at this nice right triangle, we can try to find a connection. And what do you think? Can you give me one, like at least one connection? I can tell you we need four equations. Like how we can connect using any trigonometric identity, any theorems that you may be thinking of, okay, to connect x, y, r, and theta. That's what do you think? What will be? Yes, the first one is Pythagorean theorem. That's what we will do. X squared plus y squared, I can compute r squared. Really good. This is the first one. Okay. Any other? Because we need 4 of them. Okay. What do you think? Theta. We can definitely involve theta. Involving theta in the right triangle means involving trigonometric ratio. What ratio we're looking at if we want to involve theta, y, and r? Who can tell me that ratio? Sine. I can maybe write here. Sine theta is y over r, which I can say y is defined as a r sine theta. Okay? What about theta x and r? Of course, cosine theta is x over r. X is r sine theta. Okay? And let's say theta and x and y. Theta and xy, tangent. That means tangent theta is defined as a y over x. Okay, and all of these equations are the must equation. We have to remember them. Okay? Because if you will try to convert on the test from polar to Cartesian, you will look at these equations. Okay? Actually, did I type the, oh yeah, I type on the other side. Let's look at this. That means these 2 equations are good to compute x and y if r and theta is given, right? Obvious. This one are the other way. If the x and y is given, we can compute r and theta. Yeah? That means that's what we have to know them. Let's try to convert something. Convert the point to pi over 3 from polar to Cartesian. Okay, that means polar coordinates are r, theta, and we have 2, that's theta, and pi over 3. And what we know? We know that x is equal to r cosine theta, y equals to r sine theta. And let's compute. This is 2 cosine of 60 and sine of 60. Done. What is cosine of pi over 3? Unit circle, yes, unit circle. Cosine of pi over 3 is 1/2. 1/2 times 2 is 1. I know, it's end of the semester, we're a little bit slower. Sine at pi over 3 is square root of 3 over 2 times 2, square root of 3. That means my corresponding point in the, let's say, Cartesian is 1 square root of 3. And we may check if this is correct, because 1 and square root of 3, it's more than 1, it's somewhere here. And this looks like a point in the first quadrant, because that's 60 degrees. And if we will compute from the Pythagorean, the distance is probably, it's definitely 2. Okay? It's definitely 2. Okay, that means that's definitely true. And converting from the polar to Cartesian is a little bit easier because, you know, we only have one output. Converting the other way, we have to be careful, and I will always plot and check. Even on the test, if you will have just the list of the point, of the coordinates, always plot and check if you at the right place. Okay, that's my solution. Okay, now represents the point with the Cartesian coordinates 1, -1 in terms of the polar coordinates. Okay. We can start with arithmetic. Cartesian point is 1, -1, which of course is x and y. And we know this r is cosine theta, x is r cosine theta, y is r sine theta, and then we have x squared plus y squared is r squared, and tangent theta, it's y over x. And what I will recommend, if you have this type of question, always write down for yourself all of these equations. Okay? Because you will see like how you can manipulate. Okay, and probably the third and the fourth are helpful in this time, because I have to find a polar, r and theta. Okay, let's find r. R is x squared plus y squared. 1 squared is 1, -1 squared is also 1, r squared is 2, and now taking a square root, I have positive and negative. Okay, you remember, because I can define my point using a positive or negative. I have to just adjust an angle. And we can find an angle, but I would like to see where we are, in which quadrant. 1, -1, 1, -1. We are actually here. And we will need that angle. If this is 1, -1, the same distance, you probably know. Do you know that angle, even without computing? Because it's exactly in the middle. It's the 45, the multiplicity of 45, which, yes, I'm happy to write negative pi over 4, the clockwise direction. And I can say negative pi over 4. And done. We do have one representation. But what I want actually 4. 1, 2, 3, 4. 2 with positive, 2 with negative. Okay, but now we did use this equation. Now I will use tangent. Tangent theta is y over x, -1 over 1, which of course is 1. -1. And tangent for what angle is 1? Of course, pi over 4. But negative, tangent is negative in the second quadrant, which I can say 3 pi over 4. And tangent is negative in the fourth quadrant, which we can say negative pi over 4. Or I can actually use my counterclockwise direction, 1, 2, 3, 4, 5, 6, 7 pi over 4, which is the same. Hang on, let me write this way, because that's the fourth quadrant. That's the fourth quadrant. 7 pi over 4. And also, from the second quadrant, which is this, I can use the negative notation. I can go this way. 1, 2, 3, 4, 5, but negative 5 pi over 4. Right? So we can see we may have a positive notation or negative notation. And having a positive notation, I will, no. I mean for the positive radius, okay? Positive radius, I will always plot the points in the same quadrant that is the angle. Negative pi over 4 is the fourth quadrant, and we correct. But fourth quadrant also could be defined, that angle, as a 7 pi over 4. Okay? 7 pi over 4, positive, and this is still the same point. Okay? And then thinking about the negative, I have to think about negative radii. I have to think about that angle, because that angle and the negative notation for the radius we will jump to the fourth quadrant. And this angle is 3 pi over 4, or negative notation, negative pi over 4. 3 pi over 4, that's the second quadrant, but we are in the opposite, fourth. And negative 5 pi over 4, it's also a second quadrant, but we are negative, radius is jumping here. As we can see, that's the problem, or maybe extra challenge, that for one Cartesian point, we have infinitely many polar coordinates. Okay. Also, you can pause the video and practice. Okay, let's reach maybe a few curves. Yeah, that's my solution. Okay, that means now we have to know, this is just a note. This is just the same slide. Okay, now I would like to, still in this session, to draw a few polar curves. Let me remember, if we had the point like x, y, the Cartesian, or let's be consistent, I will put Cartesian x, y, then we had like function y, which depends on x, for example. Or sometimes we're not really using very often that notation. Function f, x is the independent, y is dependent variable. But we know we will have a function, okay? The equation y in terms of x, or sometimes x in terms of y, depends if it's not a function. Okay, that means we will do exactly the same. The polar curves will be defined like this. The radius in terms of theta, r in terms of theta, r equals to f of theta. Okay? And now, based on some equations, you will recognize the shape probably right away. But let's start with plotting the points, connecting them, and then get the shape for the particular equations. And let's start with, this is actually a beautiful polar plane, right? We can see not only 0, 90, and 180, and 270, we see more angles. Yeah? And then we can count the distance from the center. Okay, let's start with some basic or maybe simple equations. For example, this one, r equals to 2. What do you think? What shape will give me this equation? Doesn't really matter what's the angle. Angle, it could be like always the radius, the distance from the pole must be 2. we can start plotting. Let's say this is 2. That's the distance for, like for 0 degree is 2, for 1 degree is 2, for 3 degree is 2, and so on. For every single degree, the distance is 2. That means what is the shape? I can write this is 2, this is this. Of course, is the circle. The circle is the circle. Now, if I will ask you to convert the whole equation from polar to Cartesian, you will write this. X squared plus y squared is r squared. X squared plus y squared is 2 squared 4. And we know that this is the equation of the circle. Okay? That means this is simply an equation of the circle. And now we may have any. Radius could be 1, 2, 4, 1/2, any. This will be a circle with the center 0, 0, 0, and the corresponding radius. Okay, you know the first equation. Now, let's look at this one. Sketch the polar curve, theta equals to 1. Theta equals to 1. Now the same, radius, radii could be any value. I have to just find that angle. And of course, this is like one, it's not a degree. It's not a degree. It's the 1 radian. 1 radian is like around 60 degrees. Yeah, you probably remember a little bit less, because if I will rewrite that 1 as a pi over 3, thinking that pi is 3. Yeah, we know that pi is a little bit more, but 3 over 3 is 1. That means I can say pi over 3, and pi over 3 is just 60 degree. That means this is my 60 degree, and I will make a longer line in the opposite quadrant. And now if the radius could have any value, the distance from the pole could be any value, 1, 2, 3, 4, 5, 6, like any number, or -1, -2, then I will cover the entire line. That means this is simply a line. Yeah, that's just the line. And we can even find the Cartesian equation. I will use this, tangent theta, it's y over x, which means tangent pi over 3, it's y over x. Tangent of 60 degrees is square root of 3. And solving for y, we have square root of 3x. Just the line with the x-intercept 0, 0, even if I will add. And the slope, square root of 3. Yeah, thinking about x and y. Yeah? That means that's the way to convert. Okay, but now let's have r and theta at the same time in the equation. That's the solution. Okay, that's more proper. Polar equation. Let's sketch the curve with the polar equation r equals to 2 times cosine theta. Yeah, and find the Cartesian equation for this. We will try to convert. R equals to 2 cosine theta. Okay, that means now the radius, the radii are changing with respect to the angle. And we will try to compute. How can I do this? I will find a few points, theta, and then we will compute r, 2 times cosine that theta. Okay, and let's say 0 degree, pi over 4, pi over 2, 3 pi over 4, pi, 3 pi, okay. Maybe I can add a few points for 5 pi over 4, 3 pi over 2. Yeah, I'm just trying to get these points, these, not this, 45. Like find the distance, the radius, and not this one, 45. That's what I'm trying to list. And if I'm going 7 pi over 4 and then 2 pi, okay, we will go around. That means for these corresponding angles, I can even draw them. I mean, we see them. We will compute the distance, the radii. And I just pick the 45. And we know how cosine behaves. It's like more like circle. Okay, 0. Cosine at 0 is 1. 1 times 2 is 2. That means for the 0 degree, for the 0, which is this one, the distance is 2. Let's say this is 2. Okay? Now, cosine at 45 is square root of 2 over 2 times 2 is just square root of 2. Cosine for 90 is 0. And then for 3 pi over 4 will be negative root 2 over 2, but the 2 is gone from the denominator. Cosine for pi is again 0. Am I right? No, it's negative 1. It will be negative 2. And then 5 pi over 4 is square root of 2 over 2, but it's the negative quadrant. And then this is again 0. This one is positive, square root of 2 over 2, but multiplying by 2, and this is 2. Okay. And that means now let's see, for 0 degree, the radius is 2. For 45, okay, for 45, the distance is square root of 2. That means it's a little bit less. Probably I will go square root of 2. And then for 90 is 0. That means I have to go this way, 0. And see, that means this is probably, if I will find all of the values for like 1 degree, 2 degree, 3, 4, 5, like all of them, I will plot all of these parts. Okay, that means it looks like a half of the circle. But now, what is interesting? Can you see the situation? The 3 pi over 4 is the second quadrant. And we know that the cosine is negative in the second quadrant. Correct? All of the values of the cosine function in the second quadrant and actually in the third quadrant are negative. What this means for us? We will not plot a single point in that quadrant. Because having a negative radius, we will plot in the opposite quadrants. That we can see that the distances are the same. For 3 pi over 4, the distance is square root of 2, but actually negative square root of 2. Instead of plotting here, I will plot in the opposite. That means I will plot here. This is negative square root of 2 for 3 pi over 4. And then for pi, the distance is negative 2, which means I will be on the opposite. And I will reach this. That means I will have that curve. And I am just here. And since, again, the third quadrant is all of the points are negative, I will plot them on the opposite quadrant. I will trace the same part, what I had in the first quadrant, and the fourth quadrant is positive, and I will trace the same distances which I had as an output from the second quadrant. Probably this looks so complicated, but I can tell you it's really easy, and especially when later you will kind of like recognize, and get the idea, because cosine theta, again, it's positive in the first and the fourth quadrant. That's the reason that I only have the points here. Okay, that means this is actually a circle with the center 1 and the radius 1, like the distance, the diameter is 2. And I can show you that's the solution, that's the explanation. Okay, but we can see no points because they are negative in the second and the fourth quadrant. I mean third, okay, second and the third. Okay, let's If you have any question, you may ask me. I know that it's new topic, and I promise I will add lots of practice with Kasia videos, because we have to know how to, we have to be confident. Okay, now I have similar, but sine theta. Okay, and what do you think? I can tell you that it's also a circle. It's the circle, but which quadrant I will plot the points? Who can tell me this for the sine? Okay. I can do the same thing. Of course, the circle will be placed with the just with the first and the second quadrant, because sine is positive. Like we can do the same thing. 45, 90, 3 times 45, and then pi, 5 times 45, and then 270, 7 pi over 4, and 360. And radius is just defined as a sine values. 0, square root of 2 over 2, 1, square root of 2 over 2. And that we can see, I will have 0, and then I will go to the square root of 2 over 2, and then 1. This is 1. Okay, something like that. And then again, come back to square root of 2 over 2, and come back to 0. It should be nice, yeah, nice circle. And all of these values are actually negative. Okay, I can find the values corresponding to square root of 2, which means I will not plot any points. I will project them. I will move them 180, yeah, in the opposite quadrants. That means having this equation, you only have a points, a curve is placed in the first and the second quadrant, because sine is positive there. And I have, yeah, that's the thing. And I have this summary for the circles. That means this is the first group of polar curves. We have maybe 5 of the groups, which probably I will not have enough time to finish today, but I will finish tomorrow. But let's see this one. If r is a constant, like any constant, this will be that circle, placed like that. If r is defined as a sine theta, this will be the a value. It's the circle in the first and the second quadrant. A cosine theta, that's a diameter, is the circle in the first and the fourth quadrant. That will make sure that you start building your reference page, the formulas for the polar curves. Okay, that we know circles. And let's maybe do one more curve for today, okay? Because we do have more, which probably the first 15 minutes of tomorrow's session, I will keep working on the polar curves. But we know circles, definitely. Yes, this one is interesting. And this will be the last one, okay? I promise. That's the last thing for today. Sketch the curve, the polar curve, defined as r plus 1, r equals to 1 plus sine theta. Okay, that we can do the same thing. I can try to build the table. I can try to pick the values for angle like 0, 90, 180, 270, and compute the corresponding radius. But what we can do, we can kind of trick a little bit this equation. For 1 second, I can think that this is y and this is x. Okay? And we know how to plot the normal Cartesian function, sine of x shifted 1 unit up. Okay, we can see this is sine of x and it's shifted 1 unit up. Okay, that means all of the y values will represent the radius, the radii. Okay, that we can see for 0 degree, because on the x-axis we have angle. Okay, on the y-axis we do have a radius. That means, for example, for the 0 degree, the radius is 1. For pi over 2, the radius is 2. You can see we don't even have to write it down. We kind of like, I'm in the table. We see from the graph. Yeah, that's the radius. For pi, it's again 1. For 3 pi over 2 is 0. For 2 pi, it's again 1. Yeah, let's make a nice easy. And of course, we can see how it's increasing between 0 and pi over 2, and then decreasing, and so on. We see the nice behavior of the radii. Okay, that's what we did. And let's start taking these points and plotting in the polar plane. And what we will get. Okay, I will not maybe draw the lines, or maybe I can make a little bit, just the main one, because I like to see. We don't have to, but let's see, that's at least the main angles. Okay, that means for 0 degree, the radius is 1. I can say 1 is here. Now I moving from 0 to pi over 2, which means the first quadrant. From 0 to pi over 2, I have to increase that radii up to 2. Can you see? I will make longer and longer and longer, and 2. That means I will do something like that. Yeah, they are like longer, 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 and 2. That means these lines are here. Yeah, because we're looking differently. Let me remove it. Okay, now what I have to do in the second quadrant, yeah, that's the first quadrant. This is the second quadrant. In the second quadrant, I have to do kind of like a mirror image. Yeah? Decrease them to 1. I will decrease to 1. Okay. Now I have to still decrease to 0. Decrease to 0. And then mirror image, increase to 1. Okay, even, yeah, it's not bad. That means this is the shape. And we do have a special name for this shape. What do you think? What reminds you this shape? I mean, it's kind of upside down. What do you think? It's something like that? Yes. Yes, it is the heart. And of course, we're not naming this heart, but we're using a Latin word. And probably you will know the word. Do you know what's the name of the heart doctor? How do you call the heart, the doctor for the heart? Yes, that means this shape we call cardioid. I know that is the cardiologist, but cardioid. Okay, I think cardioid. It's definitely the good spelling, of course. My pronunciation could be too Latin or too Polish, but it's the name of that shape is the cardioid. Okay, cardioid. And what we may have different position of this cardioid. That means we may have the heart placed this way. We may have the heart placed like this way. We may have the heart placed sideways or the other way. Okay? Yeah, that's we can see that will be the cardioid. And what is the difference? The difference will be because the general equation is 1 plus or minus sine theta, or the other one it's 1 plus or minus cosine theta. Okay? That means 1 plus sine theta is this. 1 minus sine theta will be opposite. And cosine, because what is all, we will probably tomorrow, because that's maybe too much, but that's how we can, I can tell you that all of these equations, 4 of them, okay, will give us that shape, cardioid. Okay, and I will give you a little bit more details tomorrow for this. But do you think we can try to match the equations? Because that's supposed to be my last. Because you can see that's definitely based on that equation. I really want all of my students to recognize that this is the cardioid, it's the heart, okay? Because it's 1 and 1 sign, because this is also important. That coefficient must be the same like that value. Yeah, that means it's 1 minus 1 sine theta, 1 plus 1 sine theta. I will remove this. Okay, that means we did, which one we did? Oh, 4. We did plus, okay? That means second equation is this one. Oh, I can write it actually down. 1 plus sine theta, okay? Okay, that's we have the second equation. And what do you think? 1 minus sine theta? Which equation will be oh yeah, we have the solution. D will be 1 minus sine theta. Really good. And now cosine A. Joe, what did you write for A? 3. This one will be 1 minus cosine. We can double check, and this must be 1 plus cosine. Because what we can do, let's take 1 plus cosine. We can simply check, like really quickly, what will be the value of the radius, because we kind of know the general shape. But what's the value for the radius if angle is 0, if angle is 90, if angle is 180, 270, and 360, not 3, 2 pi. Okay, cosine at 0 is 1. 1 plus 1 is 2. And we can see we do have 2. Now, theta is 90. Cosine at 90 is 0. 0 plus 1, it's 1. And it is 1. And you see we have to go to 1. And then pi. Cosine at pi is negative 1. Negative 1 plus 1, 0. 0. We reach 0. And then 3 pi over 2. Cosine is 0. 0 plus 1, it's 1. We have 1. Of course, this should be positive 1. Oh, no. It's probably the Cartesian. Everything is positive, is the distance. Okay, and 2 pi is 1. 1 plus 1, 2. We did come back to 2. Okay? That means I can maybe make bigger dots. We have to just check that dots. Yeah, that means this is definitely working. And you can check all of them. For sine 1 plus sine theta, we did like proper job. But now, since you know the shape, you can just check always the main 4 angles. 0, 90, 180, 270, and 360 again. The same like 0. Okay, I will switch on. Well, okay, I'm here. That means I will finish on this beautiful shape, cardioid. We still have other shapes, which I will start the session tomorrow. And then I will add the areas, because we have to know, for example, how to find the area of the region which is bounded by the heart. Okay, the area of the heart. Okay, let's finish today. Thank you for joining me. And yes, still please keep working. We have just 2 weeks of the classes, final test, and you can enjoy your summer. Okay, join me tomorrow for the even better shapes. Actually, the heart is the most wonderful shape. Okay, thank you and see you tomorrow.